Okay, let us begin our today's session. As you can see, I have shared a screen in front of you, which actually contains two problems, problem one and problem two. So we are first going to find mathematical model of these two problems. And then I'm going to tell you what is the objective of discussing these two problems. But the code which is written over here before the problem one and problem two, that CS6058.1 and CS6058.2.1, I have actually considered that codes, it's a kind of printing mistake. You shouldn't bother about that because actually the subject matter was in different course curriculum, and that was the subject code. You can consider this problem one to be your, say for example, mm401.1, and second one is mm401.2. Now that is different issue. It is related to course file, etc., etc. So it is not our point of discussion. The main important point is that there are two problems in front of us, and we are going to find the mathematical model of these two problems first of all. After that, I'm going to stop sharing this particular screen, and I'm going to go to the whiteboard where we'll do some other mathematics. So I ask all of you to copy this particular problem, or you can take a screenshot of it would be better if you take the screenshot later, because I will be writing the mathematical model on the page itself. So along with my solution, you can take the screenshot or take the pen to note down this particular problems in your copy. That would be, I think, better. Let us first try to solve problem number one. The problem number one, let us read what it is saying. At a cattle breeding farm, it is described that the food ration for one animal must contain at least 14, 22, and 1 units of nutrients capital A, B, C respectively. Two different kinds of fodder are available. Each unit weight of these two contains the following amounts of the three nutrients. Each unit weight of these two. So there are two different kinds of fodders. Okay. Contains the following amounts of three nutrients. Now a chart is given. In this chart, it is written that 1 unit of fodder one contains 2 is the value for nutrient A and fodder 1. 2 units. Fodder 2 is 1 unit, nutrient A and fodder 2. So we have got this chart which is in front of us. Now the question is, it is given that the costs of unit quantity of fodder 1 and 2 are 3 and 2 monetary units respectively. Formulate a linear programming problem in terms of minimizing the cost of purchasing the fodders for the above cattle breeding farm. So as you can see, I have highlighted the relevant parts of this problem, which will help us to get the variables, the feasible variables, and as well as the constraints and objective function, and we will be able to assimilate them together to write the mathematical model, which will be a linear programming problem model, LPP model, because the variables will be linear. Now, with respect to the given problem, let us assume y1 unit units of fodder 1 and y2 units of fodder 2 are considered. Okay, I'm writing in short. And we want to, and it is given that the cost of unit quantity of fodder 1 is 1 and unit quantity of fodder 2 is 2. So from this line, we get the total cost to be, if each unit quantity of fodder 1 costs 3 monetary units and each quantity of fodder 2 costs 2 monetary units, and we have assumed y1 units of fodder 1 and y2 units of fodder 2, so therefore the total cost will be 3y1 plus 2 y2 monetary units, but we don't have to write the units over here, because linear programming problem is always free of units. We only consider the values and the constraints and the coefficients, but we don't consider the units. Okay, so we'll just write 3y1 plus 2y2. And our job is to formulate a linear programming problem in terms of minimizing the cost. So obviously it says that it is a minimization type. It will be a minimization type of LPP. Only thing what we can do is that we can name this total cost to be Z. And by this objective, we can write our objective function as, min Z is equal to 3y1 plus 2y2. Min Z equal to 3y1 plus 2y2. Min Z is equal to 3y1 plus 2y2 is the objective function of the given LPP. So we have got it, and we can name it as 1. Let us try to find out the constraints. Now, obviously, since we have considered y1 units of fodder 1 and y2 units of fodder 2, these variables y1 and y2, obviously they are non-negative. Okay, so it is quite obvious from our assumption. So immediately we can say that y1 is greater than or equal to 0 and y2 is greater than or equal to 0. We can name it as equation 2. So we have got our non-negativity restrictions. Now, let us try to find out the constraints. Now you see that it is written that one animal must contain at least 14, at least. This term is very important. So let us highlight this. At least. Now, one animal must contain at least 14, 22, and 1 units of nutrients A, B, and C. Okay. Now, it is clear from the given condition and the chart that if we consider y1 units of fodder 1 and y2 units of fodder 2, according to this row, that is for nutrient A, we have got this constraint, which is two y1 plus y2, 2y1 plus 1 into y2, this should be greater than or equal to 14. Why greater than or equal to? Because this word at least is present over here. This is nutrient A constraint. Nutrient B constraint is 2y1 plus 3y2 greater than or equal to 3. And nutrient C constraint is y1 plus y2 greater than or equal to, or sorry, just a minute. This should not be equal to 3. This is, sorry, just a minute. This is 22. And y1 plus y2, this should be greater than or equal to 1. I'm taking the value from here. So this is nutrient C constraint. Everything has been written, every condition has been mathematically formulated, and if we assimilate them together, we will get our linear programming problem. So ultimately what you can write it as min z, which is 3y1 plus 2y2 subject to these conditions, and y1 y2 greater than or equal to 0. Let me copy this in my copy also, because after doing these two problems I have to do the board work, then I shall require this thing also, this inequations for me to explain to you. Okay, I have copied it. So we have got our linear programming problem of the first case. Now let us do the second problem. Okay, I hope that you have copied already, or you have taken the pic of this particular screen, because if I scroll down, my writings will move downwards, and it can block the view of some of the printed materials. So I'm going to erase whatever I have written on the screen. So just I'm giving you 30 seconds, you just take a screenshot of that, or you can quickly write it in your copy. So this is my mathematical model of the first problem. Okay, so I'm erasing it. Okay, so let us now start the second problem. Now, the second problem is saying that the table below shows the amount of 3 nutrients available in the 2 fodders, along with the minimum requirement of each nutrient for one animal and the market price of unit quantity of each fodder. Okay, so the chart is given in front of you. Nutrients are there, A, B, C. 2 fodders are present, 1 and 2. Their minimum requirements are 14, 20 to 1 for each unit of fodder 1, for each unit of nutrient A, B, and C. Market price per unit is 3 and 2. Every information is given in the chart itself. The question is the problem of the dealer. It is the problem of the dealer to fix the maximum per unit selling prices. Maximum per unit selling prices of the 3 nutrients capital A, B, and C. Maximum per unit selling prices of the three nutrients capital A, B, and C, such that the resulting prices of the fodders do not exceed the existing market price. At the same time, he gets the maximum sale price. So this is the requirement of the on the part of the dealer. So we are going to find out the total selling price first of all. Now you see that if you look at the fodder 1 and 2 together, and if you consider nutrient A only, now you see that fodder 1 and 2 both are containing the nutrient A with some units in it. Okay, so we shall visualize this particular problem from each of these three nutrients point of view for the fodders 1 and 2. Now the problem of dealer is to fix maximum per unit selling prices of the three nutrients. Now the selling prices of the three nutrients I'm concerned about. The selling prices of the nutrient decide the quality of the fodders under consideration. So suppose I'm saying that I'm considering, now in the previous problem I considered y1 and y2 units of fodder 1 and 2. Here I'm going to consider, let us consider x1 units of nutrient A, x2 units of nutrient B, x3 units of nutrient C. Okay, now the selling price for each of these cases, selling price of nutrient A will be selling price. Let us write this by S dot P. Now selling price of A will be 14x1. Selling price of B will be 22x2. Selling price of C will be x3, 1 into x3. Therefore, the total selling price will be 14x1 plus 22x2 plus x3. Now we are going to, the dealer always will try to maximize his selling price. So therefore the problem is a maximization type of problem, and we can name this selling price to be, say, W, and we can write it as max W, which is equal to 14x1 plus 22x2 plus x3. So we have got our objective function. We can name it as equation 1. And obviously, immediately after that, we can write that these x1, x2, x3 units of nutrients A, B, C, they must be non-negative. So they are feasible variables. And what is given? Let us try to read the sentences one again. That the table below shows the amount of three nutrients available in the two fodders along with the minimum requirement of each nutrient for one animal and the market price of unit quantity of each fodder. The problem of the dealer is to fix maximum per unit selling prices, okay, and of the three nutrients ABC, such that the resulting prices of the fodders do not exceed. Now this line is very important. Such that the resulting prices of the fodders do not exceed the existing market price. It should not exceed the existing market price. And from this line, we can take the help of these values from the chart, and we can get that this objective function is subject to the following constraint. Subject to the following constraint. What are these constraints? 2x1 plus 2x2 plus x3. This should be now less than or equal to 3. x1 plus 3x2 plus x3. This should be now less than or equal to 2. So we have got the maximum of selling price, that is W, which is this, subject to the following constraints, such that all these x1, x2, x3, they are non-negative. So let me copy the same thing, because I'm going to stop the sharing of the screen now, and I'm going to do some kind of board work. I hope that you have already done this on your part also too, and therefore I'm going to stop now. You can take the screenshot of this, okay, and I'm going to stop sharing this PDF file, and now I'm going to go back to the whiteboard to do some board work. So I'm erasing. Okay. Now from this problem, these two problems, we have actually, if you look at the problems carefully, you have seen that the original problem is same. This problem is a problem of fodders versus nutrient, or you can say it is a problem of cost versus selling price, or you can consider it to be a problem of minimization type versus maximization type. The problem has been discussed from two different perspectives. Same problem have been solved from two different perspectives. So our perspective one, from our perspective one, we have got a solution. From our perspective two, we have got a solution. What were the solutions? From perspective one, we got mean Z. I'm not writing the name of the nutrients and the meaning of the variables. I'm just writing the mathematical formulation, the formulated LPP. It is 3y1 plus 2y2 subject to 2y1 plus y2 greater than or equal to 14, 2y1 plus 3y2 greater than or equal to 22, y1 plus y2 greater than or equal to 1, and y1, y2 greater than or equal to 0. That is one perspective. Another perspective gave us max W, which is equal to 14x1 plus 22x2 plus x3, subject to 2x1 plus 2x2 plus x3 less than or equal to 3, x1 plus 3x2 plus x3 less than or equal to 2, and x1, x2, x3 greater than or equal to 0. So same problem, two different perspectives. From two different perspectives, we have solved the problem, and we got two mathematical models subsequently. Now, the point is, if you call this problem as primal LPP, this will be called a dual LPP. Or if you call this to be a dual LPP, then that will be called a primal LPP. So we can actually get one from the other. Okay, so same problem has been considered. From this problem, we have got two different solutions. One solution, if you consider this solution to be a primal problem means your primary problem, then the other solution will be called it's a dual. If you say that no, I'm not interested in perspective 2, I'm not interested in perspective 1, I'm interested in perspective 2, then perspective 2 becomes your primal problem, then automatically perspective 1 becomes your dual problem. So the theory which I have described is known as theory of duality in LPP. Theory of duality in LPP. Now you see that we'll try to technically analyze the different parts of the given problem. Let us try to analyze the technique, the similarity and dissimilarity between the two problems from technical point of view. Carefully observe. Without any loss of generality, I am considering this case. I'm considering this to be my primal problem and this to be my dual problem. Because I actually solved this one. There is no reason in assuming that, because I did so because I solved this problem first and that one second. So therefore, I'm considering this to be my primal and that to be my dual. You can just consider the opposite. Okay. What I observe is that if I carefully look at the problem, I observe that if my primal problem is a minimization type of LPP, my dual problem is a maximization type. So min becomes max or vice versa. So if the problem in primal is min or max, then the problem in dual is max or min. This is my observation number one. Observation number one. We have got two different variables. Here we have considered the variable z, and here I have considered the variable w. Obviously, from the contents of the problem, you have understood that one variable is defining the total cost and another variable is defining the selling price. The two different variables is having two different meanings. Okay. Also, you observe that all the inequalities which were greater than or equal to types are becoming less than or equal to type. So my observation two is greater than or equal to becomes less than or equal to, and vice versa. Now here a question, this point is important. Here a question may come to your mind that you know that in an LPP, equality symbols are also present. So you can ask me immediately that what will happen if equality symbol is present? Will the dual will remain same as equality? Now that thing will be discussed in the session 1, not now. What other observations can we make? You see that the number of variables which was y1 and y2 in the primal problem, the number of variables in the primal problem and number of constraints in the dual problem, they are same. How many variables are there in the primal? 2 variables are there in the primal. How many variables are there in the dual? How many constraints are there in the dual? 2 constraints are there in the dual. Now look it from the dual's perspective. How many variables are present in this particular problem? Dual, 3 variables are present in the dual. How many variable constants are present in the primal? 3 constants are present in the primal. So my most important observation is noted as observation 3. So we write it as number of variables in primal dual is equal to number of constraints in dual primal. Okay, so you see that these 3 observations we can quickly make from the problem and the solution of the problem. One last observation that I'm going to make is the following. Look at the coefficient of the variables in the objective function. So the coefficient of y1 is 3 and coefficient of y2 is 2. Now these coefficients have become requirements in the dual. Here you consider the coefficients 14, 22 and 1. 1 is present over here. Let us write 1. Let us put a circle around. So 1 is present over here. And now you see the coefficients of the variables present in this objective function has become requirements in the primal. So my last observation from the above analysis is that we can write it over here. I'm erasing this portion. Okay. My last observation is the per unit contribution, of the variables in primal dual becomes requirements in dual and primal. Now, since we'll be sitting for the online examination, okay, so these points which I have noted down over here, these 3 or 4 observations which I have noted, these observations are actually very important. And if you can recall the problem, you can memorize you can memorize these particular points over there. If you don't understand the problem, if you forget this particular problem, then you will not be able to memorize these points. And these points, from these points, the MCQ type of questions can also be asked to make you confused. We can I can say that number of variables, which of the following statement is correct, and I am giving you the 4 observations as statements. One observation is actually can be put in a wrong way, and you have to identify which one of them is correct or which one of them is wrong. So you have to read this out carefully. One last observation we can make from here, and this is a very vital observation that I'm going to make. Now, if I'm considering this to be primal, then that becomes my dual. Now you can say that what if this, suppose this problem is my dual problem, and from this dual problem I'm going to find out what primal problem is. Okay, so if I can say that if this is the primal problem and this is the dual problem, then I can make this conjecture that dual of the dual problem will be the primal problem itself. So this is actually a theorem which I have just noted down. The dual of the dual LPP is the primal LPP. The proof will not come in the examination, and there is no scope of writing proofs in the examination, you know, in online examinations, because the questions will be of MCQ type and numerical based and concept based. So, but this proof is very important, and we actually used to do it in the class. Okay, right now I'm avoiding this because there is no meaning of writing the proof, but you have to remember the result itself. Its result is very important. With this, I'm going to conclude my first session. Let's meet in the second session.